Welcome to Black Hat Briefings, held November 21st through the 22nd, 2001 in Amsterdam. This is videotape number 15, Smart Card Security.
It's been a long day. I'm glad that you're still here. I'll try to make it worthwhile. My name is Marc Witteman. I'm going to tell you a few things about smart cards in this last session of today. I guess you'll find the title of my presentation a bit pretentious, but I'd like to encourage you to ask as many questions as you like, so I'll try to make it through. There are roughly 3 topics that I'd like to discuss. First, it's about secure communication. This is rather basic stuff, but I think it's helpful in understanding what smart cards are about. Secondly, I'd like to go into smart card issues, how they work, concepts, applications, architecture, and finally we'll discuss security issues, how the security works, which threats there are, which attacks, and how we can counteract them. If we're talking about communication, there are always a few threats. I'll just mention a couple of them. First of all, we can consider confidentiality. If there is unauthorized disclosure of information, your confidentiality gets lost. A second threat relates to integrity. When there is unauthorized modification of information, your integrity gets lost. And thirdly, with respect to authenticity, unauthorized use of service. These are 3 things that we would like to avoid as much as possible. And cryptography may be an answer to that. The objective of cryptography is to give trust in the authenticity of a message or the sender, in the integrity of the message, and confidentiality of a message. And this all works by using an algorithm which is based on secrets shared between participants in a scheme. To make this all a little bit clearer, I try to give a couple of examples how it works. Suppose we want a confidential communication. We're going to use encryption. The blue vertical line is the interface over which we communicate, and from the left to the right we're trying to transfer a message. And at the left side we encrypt the message with a secret key, so the message goes encrypted over the untrusted channel, comes at the receiving party, who uses the same key to decrypt it and get the message again. If we're looking at message authentication codes, which can protect your integrity, the scheme can work like this. If we send a message again from the left to the right, we send both the message and an encrypted version of the message. And this encryption we call the message authentication code. At the receiving party, the same message is encrypted again, and we should have the same message authentication code there. We compare the both MACs, and if they are equal, then we should be sure that the message is indeed coming from the other party that we trust. Finally, electronic signatures for authentication. This is also known as a challenge response procedure. The sending party sends a challenge to the other party. The other party encrypts the challenge and sends the response back. And in the meantime, the sending party has encrypted the same challenge and compared the both responses. Now this is something we can use for strong authentication, which is completely different from password authentication, password authentication is static, uses the same data all the time, and can be considered as a weak form of authentication. This is much stronger. Some of the principles of cryptography. We'd like to base the cryptography on the secrecy of one key. And we use strong algorithms, and that means that it's difficult to guess the key from message ciphertext pairs. It also means that if we change just a little in the message, that I can change a lot in the ciphertext, so there's no correlation between the two. And the key length should be large enough to avoid brute force attacks. Now, if we would consider an algorithm with 1 million possible keys, it would be no problem to attack this algorithm with today's computing power. So we really need very long keys, and with long, I'm talking about keys that are longer than 2 to the power 56. That is the length of the well-known DES, which has been attacked quite a few times recently, so we should go up. And for public key, we should go above 1024 bits. There's one important principle defined by Mr. Kerkhoff, who says that the strength of the cryptography should reside in the secrecy of the key, not in the secrecy of the algorithm. This is something most people agree upon, but now and then we still see that vendors use proprietary algorithms, let's say security by obscurity, for their own reasons. Classical cryptographic algorithms use very simple mechanisms like transposition, which is a mixing of the character sequence. So suppose we like to send a word of 3 letters, we exchange the sequence of these letters. Substitution means changing one character by the other one. And polyalphabetic substitution means changing this substitution all the time. Each of these classical systems can nowadays easily be broken using language statistics. A very simple metric is the fact that in most Western languages, the character E is the most frequent character. So if we use a classical encryption system, we can use this idea to break the system. These classical systems were developed thousands of years ago. I think Caesar was recognized as the first one to use them. But only in last century, I think we really got a couple of new, much stronger ways of cryptographic algorithms. Today, we see 2 kinds. They are known as secret key versus public key algorithms. The secret key or symmetric algorithms use repetitive permutations and substitutions of bits. And examples of that are the DES, triple DES, and more of them, but also the new AES algorithm, which was just standardized. On the other hand, the public key algorithms, who in fact use a public key and a private key, they're all based on mathematical calculations. RSA and a few others are examples of that. We see often that crypto systems use a combination of both. Both types of algorithms have their own advantages, and for instance, PGP uses both public key and secret key. Now, what is quite important, as I said before, is that the secret key or the private key is carefully protected, because our security depends on this key. Now, if we would use something like PGP in an unsecure environment, like a PC, then we are really fooling ourselves, because we may have secured the communication for some time, but everybody who can get access to the machine on which the private key resides can just break the key ring, which is only protected by a simple password. So we really like to have a safe place to store our private key. And a good suggestion for that is a smart card. What is a smart card? A smart card is a microcomputer. It's a small and personal and supposed to be secure device. It can store data like keys, PIN codes, but also balances of electronic purses, personal data, and so on. And it provides a whole bunch of cryptographic services. It's worth noting that smart cards are not so expensive. I think today you buy smart cards in the range between $1 and $10. So they're really cheap. And they are getting quite popular. Maybe not everybody of you ever saw smart cards, but if you look at the picture there, the golden thing, that's actually the smart card chip. And I think today we have in this world over 1 billion smart cards. So it's a huge market. I will just go briefly through the applications to get an idea what we're talking about. So there are quite a few application areas. Let's just go through them. I think the absolute killer application at this moment is GSM. Every GSM phone in this world has a smart card in it. It's the so-called SIM card. And I've been told that the smart card manufacturers have produced over 1 billion SIM cards already. Also in the Netherlands here, there are more SIM cards than inhabitants. It's not like that everybody does have a GSM phone, but some people tend to change their phones or their provider regularly. Another application is retail. Things like vending machines, loyalty programs. In the Netherlands, it has been used for a couple of years, electronic purses, but it's not really very popular. But the thing that is popular in other countries is for entertainment, pay TV. There are a lot of countries where pay TV is offered for commercial prices, and you use a smart card to be able to view specific channels. There's also a lot of hacking and a lot of fraud in this area. Transportation is something that is coming. Things like electronic road pricing, parking, and public transport. I think it's not used so much yet, but it's growing. Healthcare can be quite important. Suppose you get a heart attack, they bring you to the hospital. If you have a medical card containing your medical records, a doctor can see whether you are allergic or what your medical condition is. Also, governments tend to like smart cards a lot for identification. We all know that passports are easy to copy or easy to make. So electronic passports are appealing to governments. But furthermore, we can think about e-commerce and e-banking. In the field of credit cards, there's a new development called EMV. It's a consortium of the three bigger credit card companies, and they want to add a smart card chip on their credit cards to reduce fraud. Finally, educational facilities and offices. Well, you can see for yourself, it's pretty obvious. You can arrange access control, protect data, arrange small costs, all these things. So let's now go into the smart card architecture. If you get a smart card, it may look like this. Then there is here the smart card chip, but it doesn't have to be that size. The SIM card in your GSM phone is actually much smaller. It has exactly the same chip on it, but just the plastic around it is much smaller. But these are contact cards. And there are also contactless cards, which do not need these golden contacts. They get their energy via radio waves. So it's a little bit different technology, but internally the operation is quite the same. If we look into the a contact card, we can see that there are 8 contacts, but only 6 of them have been defined. I'll briefly go through them. On the top left, we have VCC, on the top right, ground. These are plus and min of the power supply. So this is a chip that needs an external power supply. Then at the left, the next one is the reset pin. It's very much comparable to the reset button on a PC to reset the machine whenever you feel it's necessary. And on the left down, we have the clock pin. This chip runs on an external clock. Like your PC runs on a clock which may be 1 gigahertz, a smart card chip often runs on a much lower frequency, and a popular frequency is 3.5 megahertz. Then we have one connection for the I/O. All data is transferred on a serial line, and it's bidirectional, but both parties alternate in sending and receiving. So it's the smart card reader and the smart card itself. The protocol that's being used is very much similar to the RS-232 protocol. And then finally, the one in the middle at the right, VPP, it's a contact that's no longer used. It's the programming voltage for the internal E2PROM. But nowadays, smart cards have their own facilities to make this programming voltage. So, in fact, we are using 5 contacts nowadays. Any questions so far? Then I guess it's all clear to you. So let's go over the actual contents of the chip. If you think about computer chips, you probably think they have just one function. Like in a PC, you have a CPU and you have memory, and all these functions, they are in separate chips. A smart card chip is a complete, almost complete computer in itself. So all these functions are integrated in one chip. And we start with the CPU, the central processing unit. It's the heart of the chip. It does all the computational work. Some people think that a smart card is only a memory chip. It's not true today. The earliest smart cards or chip cards that we had in the field, let's say 10 years ago, they were memory chips used for counting phone minutes. But today, all smart cards have a CPU for security purposes and others. Another function is the security logic. Maybe a little bit comparable to a firewall. It's some logic that detects abnormal conditions. And one of these conditions can be a low voltage, as this chip gets its power supply from external source. The next function is the serial I/O interface. We discussed that already. It's the contact, it's the single contact with the outside world. Then we have the test logic. You have to imagine that a smart card chip contains 10,000 up to 1 million transistors. And during the manufacturing process, well, it can happen that they're not all working correctly. So we need test logic that tests all the semiconductors inside the chip. Now this test logic is not really helpful in terms of security. So what we often do after having verified that everything's correct, we cut off the test logic in a way that it cannot be used anymore. Then we come to the various types of memory. First of all, we have a ROM memory, read-only memory. This type of memory often contains the card operating system, the self-test procedures, and all things that are fixed. So all data that you need to use on the smart card, but it's fixed. So in this case, we have an operating system that we can never change. Another type of memory is the RAM, random access memory, and this is the scratch pad of the processor. Here the operating can store its stack, it can store temporary variables, it can store some buffers. It's very small. I think 512 bytes is a bit too less for nowadays, but 1 kilobyte is just about the size that's needed. If you compare that to a PC, it's almost nothing. But the big difference is, in a PC, you load any application and the operating system from disk into your RAM memory, while on the smart card you won't. You use it only for storing temporary variables. Finally, we have the E2PROM. This is rewritable but non-volatile memory. What we use there is cryptographic keys, pin codes, biometric templates, balances, application codes. This is all data that you may like to change sometimes, but it should not be gone as soon as the power is switched off. So E2PROM is the appropriate place to store that. By the way, a biometric template is, let's say, a hash value of some biological property of a person. So it can be your fingerprint or an eye scan or whatever. Finally, we have the data bus. And the data bus is just connecting all these functions together. Now, there's something important here. If we know that the serial I/O interface is the connection to the outside world, you may get the impression that via the serial I/O interface we can directly read the E2PROM or any of the other memories. This is not true. All data transport is governed by the CPU. So the CPU does all the data transport, and the CPU will read the serial I/O interface and then decide which data to transfer. But it's not like that an external party can access the memory at arbitrary places. Of course, the data bus is very interesting in terms of attacking. All data that's being transferred goes via the data bus. So this is what a chip looks like. Let's just try to identify a couple of things. Here at the border, we have the so-called bond wires. These are the 5 wires that go to the 5 contacts that we're using. Then here, these big areas are the E2PROM. Above that, we have the ROM. And above that, we have the RAM. Here at the left, above the middle, it's the CPU. And on top, there's the security logic and the I/O logic. What's important to realize is that the dimensions of a smart card chip are limited. They are standardized upon 5 millimeters squared. The reason for that is that a smart card often ends up in a wallet or in any other unfriendly environment where it is bended or treated in an unfriendly way. So the chip itself should be so small that it will not easily be damaged by bending. So what can we do if we want to put more on this chip and we've got only 25 square millimeters? There are 2 possibilities. Either we reduce the feature size or we go into multiple layers. Now, as a matter of fact, we're doing both. So a couple of years ago, it was normal for a smart card chip to have just 1 layer. Today we see smart card chips having 7 layers. Also, the feature size, so the size of the wires and the transistors on the chip have reduced from 1 micron a couple of years ago to 0.2 micron nowadays. So there's a migration. So there are some basic smart card security features. I would say basic because most of the smart cards have these features. In terms of hardware, first of all, there's a closed package. There's just 1 chip that does it all, and we don't have a system with all kinds of connections, just 1 closed package. The memory is encapsulated. There is no direct access possible to the memory. There are fuses for the test logic. I already told you that. As soon as we don't need the test logic anymore, we disconnect it, and they can use fuses for that. They blow a fuse, and the test logic is no longer available. And of course, we have this cryptographic facilities, coprocessors and random generators. They're quite often on board, so these are real hardware random generators. In terms of software, there are a couple of features as well. What most manufacturers nowadays do, they decouple applications and operating systems. Let's say 3 years ago, smart card software was monolithic, application and operating system was just one thing. Now we see that they separate them, and they also start separating applications. And this is mainly due to the advent of Java cards. Java cards is a standard which is derived from Java, but it is much smaller. It's a very much reduced code. There is, like in many operating systems, restricted file access. For every file, first of all, I have to tell you that on the E2PROM, there's just a file system. Like on a hard disk, you can have a file system. You can have it on the E2PROM too. And this file system contains files with access conditions. And for every file, we can set who can access it and what kind of operations we can do on it. Another nice feature is lifecycle control. Whenever the smart card is just produced, it's leaving the factory, we need to put on a lot of application data, maybe even an operating system. And this is a lot of data to be exchanged, and we need to do it fast, and we don't want to be bothered by all kind of access procedures. So in this first stage, we don't use that many access features. We just want to be able to pump a lot of data. Later on, we want to restrict it. There may be a few things that have to be changed. We have to load the name of the card holder, maybe a PIN code, things like that. So there are a few issues, a few things that we need to be to change. But finally, when the smart card goes into the field, it should be as much closed as required. So it means that nobody can read the secret keys, nobody can read the PIN codes, things like that. So this is lifecycle control. And finally, of course, we have various cryptographic algorithms and protocols that support secure communication. Okay, I'm going to move over to another subject, all types of attacks. Are there any questions so far? Is everything clear? Okay. I'll discuss three classes of attacks. First of all, the internal attacks. These are invasive attacks using high-end lab equipment, and although it sounds very sophisticated, it's not new at all. The chip industry uses this type of equipment for many years for chip prototyping, but in this situation we're going to use the very same equipment for attacking the smart cards. Secondly, we're going to talk about logical attacks, which are in a way similar to penetration attacks as we know them from the internet. We're just using let's say the normal interface to the smart card to explore its data structure, to explore its behavior, and to find holes. Finally, I'll tell you something about side channel attacks. This is a relatively new class of attacks, very, very dangerous, and it works by getting information from channels that are not intended for communication. I'll tell you more later on. Internal attacks. First of all, I have to tell you that these pictures were provided by TNO, which is a smart card evaluation lab here in the Netherlands. What kind of tools can we use? Etching tools. These are tools to open a chip, so to get rid of the plastic on top of it, to get rid of metal layers, and to etch layer by layer in order to get access to the inside of a chip. These methods are often very destructive. A second tool is a microscope. As soon as we have etched a chip, we may like to study it under a microscope and do reverse engineering. Another tool is a probe station. This is a machine with needles we can put on the wires on the chip to retrieve data or inject data. We've got laser cutters for cutting off small parts of the chip. Scanning electron microscopes, they're useful when the details on the chip get too small to see in a normal microscope, but also they're useful for seeing the behavior of a chip when it's working, because we can see some electrical fields as well. An extremely powerful tool is a focused ion beam, a FIB, which is a bit like an electron microscope in the sense that it can see the chip, but it can also be used to put new material on the chip. So we can direct a beam of material, and it can be metal or isolation, and this is, I would say, the perfect reverse engineering tool for making changes to a chip. It's quite often used in prototyping when manufacturers design new chips and there are small problems. They use a FIB to change the circuits. And, well, there are more tools. Let's see a couple of pictures. Reverse engineering. If we open up a chip, etch away the top layers and use a microscope, we can really look at the circuits. We can see the wires and we can see the transistors. And let's say somebody who is experienced in electrotechnical engineering knows how transistors are implemented in chips. He can reverse engineer such a circuit. Now this is, of course, very tedious work because we're looking now at a couple of transistors, but if there are 10,000 on the chip, you can imagine that's a lot of work. Sometimes we don't want to reverse engineer a complete chip, but just a few parts that have some sensitive, secret data on it. By the way, there are also labs who perform this service on a commercial basis, not for hacking chips, but for competitive analysis. Suppose AMD wants to develop a new chip. They ask such a lab to reverse engineer the latest Intel chip to see what the competition is doing. And in the same way, they can do this reverse engineering to see whether the competition is using any of their patents. If we look into the ROM data on the chip, ROMs are often implemented by means of ion implant. It means that every ROM cell has a physical same size, but by shooting in ions, you change the behavior of a cell from a 0 to a 1. So if we do a special kind of etching, which is called staining, we can really visualize under a microscope the bits from the ROM. And of course, this will allow us to retrieve the operating system code. This is what a submicron probe station looks like. The probe station has a microscope part, and here under the microscope there's a chip. And here we have needles which we can put on the chip. This is a close-up. In this case, we're not looking at a smart card chip, but you can see there are a couple of needles that are put on top of the chip. And if you put, let's say, 8 needles on a data bus of a chip, and this chip is using an 8-bit data bus, you can tap all the data being exchanged. Finally, some piece of art done with a focused ion beam. Here we have a fuse, part of the test logic, which was blown after completion of the test process. And we've used a focused ion beam to put a new strap of data over the blown fuse, making the test procedures available again. And test procedures allow you to retrieve all the data. Now, this all sounds quite sophisticated, but for evaluation labs, that is a bit old stuff. As you can see, the size of the features here, I think the lines are thicker than 1 micron. Nowadays it's 5 times smaller. So all these things may be still possible, but are getting much more difficult. So in the terms of internal attacks, hardware attacks, there are quite a few things you can do against it. Let's have a look at them. First of all, we can do something with alarms, having sensors that detect attacks. We can have a light sensor that as soon as there's some light observed, which can only happen when the chip is open, it erases its memory. We can have an active grid, which is like an electric fence that does not allow an attacker to go through a top layer. We can do all kinds of things to hide the functions in the chip. We can reduce the feature size. When it's smaller than 300 nanometers, it's really not possible anymore to see them with a normal microscope. So you need an electron microscope, which is very expensive. By the way, all these expensive lab equipment can be hired as well. So there are quite a few labs that offer hiring of their equipment. So it's not always that difficult. In terms of hiding, when we do multi-layer, stack a number of layers upon each other, an attacker will have a much more difficult job in reverse engineering. If we at the same time use a buried bus, which means that the bus itself is very low in the stack of layers, it's going to be quite difficult for an attacker to reach and tap the bus. We can also do bus scrambling. As this bus is so important, we can do some kind of simple hardware scrambling in which we make the data on the bus just a big mess for somebody who doesn't know the scrambling key. And we can use shields, let's say metal covers or whatever cover on top of the chip to make it difficult to penetrate. Also in terms of confusing, we can do quite a few things. When we looked upon the chip a couple of slides back, we could very easily recognize all the functions in the chip. For the newest chips, that's much more difficult because they use so-called glue logic. Glue logic is a process in which we ask a computer to transfer the complete design of a chip into one mesh of connected transistors without having any relation between position and function. And also what we see quite often is that they use redundant logic, so there are additional wires and transistors on the chip that are not really used, but are used for confusing the attacker. So I'll move to another class of attacks, the logical attacks. Although I haven't got too many slides about them, this can be quite an effective and dangerous class of attack. The reason is that we need hardly any equipment. I'd say you just need an ordinary PC and a card reader. What could we do? We could do a command scan. So try to find out all the commands that are supported by the smart cards. Smart cards have use binary coding of commands, and there's just 2 bytes allocated for indicating the command. So you can exhaust these 2 bytes, try all 65,000 possibilities. And often you'll find that there are commands supported which are not in the spec, and these are maybe proprietary, used for testing purposes or whatever. We could try a file system scan. There's a file system containing all kinds of files that should be properly protected for reading, but are they really? So if we try to scan this file system, we'll find out whether we can read the pin codes or the keys. These 2 things are nowadays mostly okay. It's really very bad if we find a backdoor here. But if we look into invalid and inopportune requests. These are attacks in which you try to communicate with a smart card using commands that are syntactically wrong. So we're using wrong values for parameters, or we're using correct commands at the wrong time. They can be pretty hard. I remember an example where a smart card supported a command that meant something like send last data again. So suppose you're in a communication and you're exchanging data and something goes wrong, you ask the smart card send last data again. So and it retransmits. Now suppose that you ask this question immediately after starting up without any data being sent previously. The smart card may send its complete memory because it's confused what you really want. So these things happen now and then. Finally, we've got cryptanalysis and protocol abuse. It's a bit different type of attack. Needs a very clear mind, understanding how the cryptography works. Example is the GSM authentication algorithm COMP 128. This was originally a secret algorithm. It leaked at some point of time, and some researchers found out that it's not completely secure, and if you collect 100,000 challenge response pairs, you can recompute the key. And well, that's something that's being done, and it's a big problem for the GSM industry. So what can we do against all these logical attacks? If you look into the command scan, you need to limit the command availability. You need to restrict and verify command coding. And you need to enforce lifecycle management. So some commands may be available at an early stage, but they need not be available in the field. With respect to the file system scan, you have to take care that the file access is restricted, and of course the file access mechanism should be tested. With respect to the invalid and inopportune requests, you have to make sure that the implementation excludes all non-valid behavior, and of course you need to test to verify the conformance then. Finally, cryptanalysis. It's been said quite often, but we really need to publish algorithms, and we really need to discuss them in order to get all the problems out before they are implemented. So proprietary algorithms are not really a good idea. And finally, we should evaluate the crypto algorithm and protocol. It's all pretty straightforward. I'm getting to the last class of attacks, the side channel attacks. This class of attacks got popular about 4 years ago, and it appears to be very powerful, and the problems that have arisen are far from over right now, although manufacturers are working quite hard. This is what it's all about. The smart card has one single pin for normal communication, but unintended, it communicates in another way as well. It transmits electronic emission about what it's doing. It uses power, it has some power consumption. It uses time for doing operations. And all these things give an attacker information. And we'll see what we can do with it. On the other hand, we can look into insertion of signals. So suppose that we interrupt the power supply for a very short moment, or we use a very strong electromagnetic pulse. It might be possible to influence the behavior and in that way attack a card. Now all these attacks, they aim at retrieving the secret keys or the secret pin codes. This is a picture of one single clock cycle. The clock is the heartbeat of the CPU. Every clock cycle, the CPU makes one internal step, and it processes instructions. So it processes machine instructions in a couple of clock cycles. Now this is one single clock cycle, and we're looking at the power consumption during this clock cycle. Here the clock cycle starts, and for a while nothing happens, but then the power consumption goes up and it slowly goes down to the end, and when the next clock comes, it starts again. Now, if we look into the characteristics of this clock cycle, you can see there are a lot of properties that might mean something. There's the peak value, there's a slope, there's a shape, there's an area, there's some time, there's a rest current. All these properties mean something. And it will probably not be a surprise to you that if we compare this clock cycle with the next one, that they will not be identical. So what does this all mean? This means that instructions in a microprocessor have a signature. Every instruction has its own characteristic power consumption. That's quite something. It means that if we are able to identify which instruction is connected to that profile, to that signature, we can reverse engineer the code. Now, it's often not as easy as that, because the changes in the power signature are not always that obvious, but they are really there, and we can see them. You can see there is a bit of noise on the signal, and the more noise there is, the more difficult it is to make the distinction. Apart from recognizing instructions here, we could also recognize data. Suppose this clock cycle is part of a load instruction that loads data from memory into an accumulator. Then you might imagine that the Hamming weight, the number of bits that are set to 1, affects the current, because a different number of ones will make a different number of transistors to switch, and it will change the power consumption. So we see that there is a correlation between the instruction and the power consumption, as well as between the data and the power consumption. Now, if we zoom out largely to a complete program, here we have a power consumption over 200,000 clock cycles. Then you can see indeed that not every clock cycle has the same power consumption, and there are really patterns that seem to be repeating. If we count the patterns that we see in this part of the power consumption, we can see that there are 16 recurring processes. Now, the number of 16 means a lot to cryptographers. In this case, we know that the smart card is running the DES algorithm. We are looking at 16 rounds of DES. So here we are at the stage that we can recognize the processes in the software. We can pinpoint the exact timing where processes take place. Now, there are a lot of next steps that I'm not going to explain in detail here, but if you introduce statistics, if you repeat these kind of measures a couple of times, you can use the statistics to retrieve exact data values. You can use these statistics to retrieve the values of keys and pin codes. And this is a very strong instrument. What we need here is an oscilloscope to measure power consumption. We need a PC. We need somebody who understands the matter and can write a couple of programs to analyze all the data. We've done experiments that show that we can retrieve keys from smart cards within 1 hour. What is important here to realize that this is not purely a smart card attack. We could do the same attack on any CPU. It could be on a CPU in your PC or in any box in the network, as long as we can measure the power consumption or we can measure the emission of power. The problem, however, is that this smart card runs on 3.5 megahertz, while your PC runs on 1 gigahertz, which is quite a bit faster, which is quite a bit more difficult to measure. So we'll probably need a whole different class of equipment, which may be much more expensive. Yeah?
Which is the typical or the maximal clock rate, for example, in a public telephone here outside?
Are you talking about telephone cards or?
Yeah, for example, when you put the telephone card,
Okay,
used to be very
all telephone cards all work on 3.5 megahertz.
how much?
3.5 megahertz. Yeah. Most telephone cards, by the way, work with proprietary algorithms. Now, something that I'm currently researching is reverse engineering of unknown algorithms. What we see here, we can use for retrieving keys of known algorithms. So if we know that it is the DES, we can use the information to recalculate a key. I'm working on a method to reverse engineer an unknown proprietary algorithm, which is of course quite a bit harder, but if you get enough information, I think this is possible. Okay, the final subject, fault injection. I already mentioned it. When you try to interrupt the power supply or introduce a electromagnetic spike, something can happen. And here we have an example. Suppose your chip, your smart card, is doing a read operation in which it tries to get the value of a memory cell. And exactly during this read operation, you dip the power supply. You reduce it to less than half. And you do this for a very short time. It can happen that the chip reads another value than was actually there, because internally there's a threshold for this read value. If we read a voltage below the threshold, we interpret it as a 0, otherwise we interpret it as a 1. So if we manage to lower the supply voltage for a very short time at the exact moment, we can establish that the CPU reads another value than that is actually there. Now, the important thing here is that we make this spike short enough that the chip just continues running. It should not crash, because if it crashes, the experiment doesn't give you any information. But if it doesn't crash and it keeps on running, it may have used a wrong value. And you can use this also to retrieve keys. A very simple example would be whenever you verify a PIN code, there is some point of time in the software that the software decides the PIN code was good or the PIN code was bad. If you're able to make a manipulation at this very moment, you can make the software believe that it was good while it was bad. Is that clear? Okay, then I'll move over to the countermeasures. They are maybe a little bit over the top right now, but I just go briefly through them. What can we do against signal analysis, so studying power consumptions? First of all, we could try to reduce the processor signal by balancing or equalizing the power, maybe shielding the emission. We can try to add noise to the processor activity. It can be both in amplitude but also time. We can try to play a little bit with the ordering, variable ordering of processes, but also try to eliminate a timing relation with the keys and the data. We can use retry counters, which is quite effective against the statistic process, because if we're using statistics, we need to repeat procedures often. If there are retry counters, we might be limited. Talking about signal insertion, we can use sensors who detect small changes in a supply voltage. A drawback here of these sensors is that it will make a chip less reliable, because if the chip is used under conditions where the power supply is just changing because of a bad battery in the relay, it should not act strangely. We can try to do a double implementation path, which means that we are going to do everything twice and compare it to see whether something went wrong. This has, of course, a bad effect on your performance. Or we can check for runtime parameter validity. So we can check whether parameters have the value which is acceptable, but also that will affect your performance. But all of these countermeasures are indeed possible. That brings me to my conclusions. First of all, smart card technology is emerging. Maybe we haven't seen it everywhere yet, but the applications are everywhere, and we will see them soon. Smart cards do enhance both service and security. However, perfect security does not exist, even not for smart cards. We've shown a lot of potential problems, and therefore risk analysis and evaluation is essential as soon as you like to use these devices. Thank you for your attention. Are there any questions? Yep.
What is the time and cost of mounting an attack?
The question is, what's the time and cost of an attack, of any attack?
Well, I mean, yeah, what an attack, or what kind of resources
Yep.
do you need to
Yep.
sacrifice
Okay.
effort on GSL?
Yep. I've described three classes of attacks. Let's start with the internal attacks, the invasive attacks. I would say an attacker may need on average 1 week to 1 month to get into a chip and get the right data out. One person. He will need a fully equipped lab with more than $1 million equipment, but he may be able to hire such a lab. If we're looking into the logical analysis, for which it is not always possible to do a successful attack, but if it is possible, it can be very cheap because the attacker needs only a PC and a simple card reader. This may take up to a week just to explore all the behavior. So if you're lucky, you can do this attack for very little money. And finally, if you look into side channel analysis, this is in the field now considered as the most dangerous type of attacks because it's much more often successful than the logical attacks. It will take you maybe $20,000 of equipment and a couple of weeks work as soon as you understand the principles, as soon as you are prepared. There's of course some issues about repeating the same attack. As soon as you have done the attack once, you can repeat it for logical and side channel analysis quite fast, in maybe a couple of hours, while for an internal invasive attack, it may still take a couple of days. Does that answer your question?
Yes.
Okay.
What do you think the impact of cordless chips will have on smart cards?
Well, we can see the impact already because the smart card hacking and smart card fraud is not new, especially in the world of pay TV. We've seen a lot of fraud already, and we know that there are even illegal labs in Eastern European countries where they copy complete chips and then sell them on the market. So what we've seen is that manufacturers have done a lot of work to increase the security of their products. 5 years ago, we saw that manufacturers used old machines, so machines that were no longer used for making the newest PC processors. They're using the old machines to produce smart card chips. Nowadays, they're using brand new machines, and the technology for smart card chips is in many ways much more advanced as a technology for other types of chips. But at the same time, I have to stress that they are not there yet. There are still quite a few vulnerabilities. It's not like that everybody can simply attack a smart card, but there are still quite a few openings.
But you see the advent of cordless chips and smart cards eliminate all of the side channel attacks.
Sorry, can you repeat the question?
Do you see the advent of cordless chips and smart cards defeating any of the
Yep.
side channel attacks?
Okay, the question is whether new smart card chips that do not need an external clock, that they can defeat side channel attacks. So this is a new development that chips do no longer need an external clock, but they generate their own internal clock.
Actually, no, I'm talking about true
Okay, yeah, so that would be one step further. Let me first answer the question in case what we see that manufacturers generate their own clock. There is a countermeasure which works to some extent, but an experienced hacker will still get through it. If you move over to chips that are not using any clock anymore, this is going to be much more difficult. On the other hand, there is a bit of reproduction in repeating a process. So if you repeat the same process a couple of times, there may be small variations in timing, but it's not that much that it will make this class of attack impossible. Any other questions in the end?
Does temperature affect any of this?
Yeah, the question is whether temperature affects this, right? I think almost all smart cards use temperature sensors. In the past, there have been some successful freezing attacks. These are attacks where the temperature of a smart card is reduced to 0 or almost 0, meaning that data that was stored in the RAM memory did not leave the chip, and in some way it was possible to retrieve this data. Also, when we bring up the temperature to a very high value, it might be introducing faults in the CPU, so that's another danger. I think all manufacturers use now these sensors that limit the behavior between minus 30 and plus 50 Celsius, something like that.
You already said that there are labs copying smart cards illegally and stuff. We saw a few years ago the smart card clone project from the German Chaos Computer Club,
Yep.
where they cloned the telephone SIM card from E2, from German provider.
Yep.
How does it look with cloning cards and copying cards? How difficult is that? Is it still working the same way the CCC did it, or how the improvement of the industry there?
Yeah, well, there have been a couple of attacks in copying and cloning smart cards. I think industry made some progress in preventing these types of attacks, but it's also related to a big installed base which is out there. So operators don't like to change all the smart cards that are in the field. So yeah, we'll see these problems to persist for some time.
What encryption algorithms are most widely used?
Triple DES, the question is which encryption algorithms are popular. Triple DES is most popular. On some cards we still see DES, but it's extincting now, I think. Triple DES is most popular. We see RSA on some cards. Some manufacturers are experimenting with elliptic curves and with the Rijndael AES algorithm, but this is just marginal. Yep. The question is how much standardization is there? Well, the answer is there's quite a lot of standards, but they are contradicting each other sometimes. So I would say standardization is still an issue, and it's probably also hampering the breakthrough of smart cards. Although if we look into operating systems, there has been a competition between 3 platforms, which is Java cards, Multos, and Microsoft Windows for smart cards. And now we've seen that Java cards is accepted by all parties. So that's, in a way, a progress in standardization. Does that answer your question? Okay. One more question. No question. So I thank you all for your attention.